There. So the last thing we did on Monday, that was the last time we met, was some stuff about graphing high-degree polynomial equations, high-degree polynomials, as long as they're factored. How do people feel about that? People feel like they want another example of just doing that? There's another one in the notes. Should we do? Let's do. So the example provided in the notes is, let's graph y equals, and I'm going to use the exact one from the notes, x squared, x minus 2 to the power of 4, x plus 1. And let's go down the list. This graph, I would like to have the correct x-intercepts. In order to sketch a graph that has the correct x-intercepts, well, you kind of just have to find the x-intercepts. Where are the x-intercepts of this graph?
0, 0.
I hear 1, 0, 0. And you got that by saying, well, if this thing is equal to 0, then x squared needs to be equal to 0. Well, one option is x squared is equal to 0. Any other x-intercepts?
Negative 1, 0.
Say that one.
Negative 1, 0.
Negative 1, 0. Any other ones?
X equals 2.
X equals 2, or 2, 0. I'm writing this way, and you're saying that way, but it's fine. All right. Feel good so far? If anything I write on the board is just like too small, shout out. I prefer writing on the board to paper, but like I get out of practice and then like I get small. All right, neat. Next thing I want to have correct is y-intercept. Where's the y-intercept of this thing? Yeah. 0, 0. In fact, I don't need to do any work. I already see a dot on the y-axis. There can't be 2. It's a function that needs to pass the Bodica line test. Local behavior. So let's go through the list. I'll do it in the same order that they're stacked vertically. Close to x equals 0. Let's see what happens. So how do you figure out local behavior? You need to remember the actual factor that corresponds to that root. And let's see, how bad is this in the way? Is it like really bad? Or is it okay? It's kind of bad. Trouble is I don't think I can make it any better. If you want to move to it, you can, because I'll try to stay over this corner a little bit. Right there, well, whatever, I can be flexible. Local behavior. Near x equals 0. I need to remember the x squared because the x squared corresponded to the intercept at 0. Now, I can just plug in zeros for all the other x's. All right. So it looks like I should see a parabola because of the x squared. Upward opening or downward? Upward. The only negative is in something to the 4th power. All right, so near 0, near the origin, I should see an upward opening parabola. So far, so good. All right, let's carry on. Near, the next one on this list is x equals negative 1. The game is the same. I need to just remember the factor that resulted in that x-intercept. So I guess that's this one. So I should see something that like crashes straight through the x-axis. It should look like a line. The only question is positive slope or negative, and to decide, plug -1 in for all the other x's. -1 squared, -1 minus 2 cubed. So it'll be a line. Positive slope or negative? Yeah, positive. And you can work out exactly what that positive number is, but I don't want to because I don't care. But my graph isn't going to be so good that I'll be able to tell the difference between a slope of 10 and a slope of 20. They're both just going to be positive slopes. It's going to be a line with positive slope. So far, so good. Close to 2, 0. Yeah.
Did I miss something, or is like the 3 supposed to be a 4 on that one, or is it the?
Don't know what you're talking about. Yes. Always was. Thank you. Yeah. Because that would have changed things, right? Like, without that ball there, it would have been negative. All right. Do you think you could just address the question for near x equals 2? Do people want me to do the walk? Cool. Well, now I'm going to stand here for a bit. Someone is going to describe to me the graph close to there. Let's hear it. Parabola, upward opening. I think I don't like the word parabola because it's like to the fourth power. And I don't have a name for something to the fourth power. Like it's parabola-ish. Yeah.
Kind of like M-shaped or like upside down U.
Yeah, it's like an upside down U, which is like parabola shaped. So I'm really being like a picky pedant when I say like parabola isn't the right word. Like if you do all the walk and you say it's a parabola, I'm not going to take points off. But like, I might talk about say it's next to a plot, it's not a parabola. Cool. We feeling good? So now let's just put something that's like a parabola but like boxier shaped. All right. That's supposed to point down. The next step in the plan is just interpolating between. So it looks like there are 2 different humps. I don't know how tall they are because I didn't do anything to try to tell how tall they are. I don't even know which one's taller. Asymptotic behavior. I think there's maybe even just like a handy shortcut to do all that walk. Like you know what the answer is, like only the lead term of the polynomial matters. But you can get the lead term of a polynomial that's factored out by just taking the lead term of each piece. And that's even like easy to remember. So this y is, well that's just an x squared, so let's leave that x squared. Does that -2 next to the x even matter if x is like 10 trillion? I mean, like, it does make a difference, but it's not one that you'd even notice at that scale. Same thing with that +1. So for really big x values, this should just look like x to the 7th. Am I getting below where is seeable? Is that okay? Okay. This room is just kind of a tragedy when it comes to actually using the block. All right, x to the 7th. I know what the graph of x to the 7th looks like. That feel pretty okay? Nice. Cool. So once you have a polynomial factored, it's easy enough to graph. Right, this took a few steps, but none of the steps were like hard. In fact, I don't know, like you could probably do a bunch of this without writing anything down, though. Like you should write things down. It's easier to make mistakes when you don't write anything. But that kind of suggests a problem. If I just give you a high degree polynomial, how do you actually find those factors? How do you factor a polynomial? Can you? Do they? These are like valid questions, and the answer is usually the answer to can you factor this polynomial is either you can't or it's too hard. And let me describe exactly why. So I'm going to go to the next page, and we're going to start in on this next section. So page 66. Let's talk about some tricks that let you solve high degree polynomials sometimes. And I'm going to start this with like a historical discussion. So if I give you a degree 1 polynomial equation, that's easy to solve. I just add the constant to the other term, divide that. Right, that's on its own. If you have a degree 2 polynomial, that's easy enough to solve. You have like the quadratic formula if you want to use the black box technique. Black boxes and you don't know what's happening inside. It just logs. Or you can use completing the square and make it easy. Sometimes you can factor. If you have a degree 3 polynomial, it turns out that back in the 1500s, is it Cardano that I said is the name to say here? My notes are over there, you have them in front of you. I think Cardano, right? Okay. A mathematician by the name of Cardano developed a cubic formula. It was developed a little bit more by a student of his called Tertullian. So you can solve any degree 3 polynomial. That's kind of nice. The reason you never learn this cubic polynomial is just because it's too big. Like if you go to the Wikipedia page on the cubic formula, there is one. Like you'll see a formula, and you can extract enough information that you can use that formula. You can teach it to a computer if you're computer-minded. But it's sufficiently long that like you wouldn't want to use it by hand anyway. I guess in the 1500s they did, but you wouldn't. There is a solution to every degree 4 polynomial equation. So there's like a quadratic formula that solves everything that's degree 4. If you want to write down that solution, it probably takes you like at least a page and a half to write down all the details. Not just why that formula is true, but what the formula even says. So it's certainly too hard to use by hand. But if you want to teach it to a computer, you could. So you can algorithmically solve every polynomial, even up to degree 4. In the 1800s, a mathematician by the name of Galois proved something really surprising happens even starting at degree 5. Not every degree 5 polynomial has solutions that can be expressed using only algebra. So what Galois showed, using basically a new field of mathematics that he had to invent, was if you do any combination of add, subtract, multiply, divide, take n through roots and raise to powers, so like things you would want to do if you wanted to like solve a high degree polynomial, you cannot get the solution of this thing in terms of those. It doesn't admit such an expression. So that's like really upsetting. That says that no algebraic techniques can solve that polynomial equation. Do you think you could still get an idea about the solutions of this polynomial equation? Say if you had a graphing calculator in front of you. In fact, like how many people just have a graphing machine easily accessible to them right now? Yeah, bust it out. Tell me about what the solutions to this equation are. notes, but that doesn't do you any good. So, but what is the x-intercept of this thing?
Well, 1.16734.
1.16? Yes. I think that's good enough for me. Wait, the next digit was 3? So we should round out?
No, I did this one, but
We should round up. And like, the rest of the graph looks like. So you can still approximate roots of this polynomial. And if you look at a computer-generated graph, you can still eyeball what the roots are. But that, about 1.167-ish, isn't exact. And in fact, none of these techniques will tell you the exact value of that polynomial equation, or that root. So that should be like kind of upsetting. I've just told you that even once you get to degree 5, you can't algebraically solve every high degree polynomial equation, but I still want to spend today and the next couple of days trying to algebraically solve high degree polynomial equations. So there's like an inherent contradiction of problems there. But we're just going to live with that. We're going to try. We'll see what we can do. There are some tricks that work sometimes. We're going to try to build them. The tricks always give information. They just don't always give you all of the information to find the solutions. At age 21, Galois died in a duel. In fact, there are some rumors that, so Galois at the time was also kind of a political rabble-rouser and thorn in the side of the, I guess at that time it would still be the monarchy. And there is definitely a rumor that this person who he got into a duel with, well, was known to be a professional sharpshooter. The rumor is that person was paid off by the French government to get Galois to challenge him to a duel, which Galois had no chance of winning. So, lesson here, don't accept duels. Unless, I don't know, maybe you like Yu-Gi-Oh! Those duels are okay. All right, cool. So, we have the situation where we can't solve all polynomial equations, but we can make progress, so we're not just going to give up. Here is the first example that I want to do. Let's solve this polynomial equation. We'll find exact solutions given a little bit of cheated extra information. I'm going to go over here. I'm going to stay above this line. Let's solve 2x cubed minus x squared minus 7x plus 6 equals 0, given that x equals 1 is a solution. And I'm not telling you where that x equals 1 came from. I'm not telling you how I know that x equals 1 is a solution. But I will tell you this. Is it easy to check if x equals 1 solves that equation? Does x equals 1 solve that equation?
Yeah.
I hear a yes. How many people took out their calculator to check that? You made your life harder than it needed to be. Plugging in 1 is the easiest thing, because what is 1 squared?
What?
What's 1 to the 5th? So I can forget all the powers. All of these x's to a power are just 1. To plug in 1, I need to compute 2 minus 1, which is 1, minus 7, so that's minus 6, plus 6, yeah, that's 0. So, and here's the philosophy I'll use. Oh, it's kind of awkward that I just erased that graph, because that graph illustrated something nice. Factorization, a factor of a polynomial corresponds to a root of that polynomial. The same thing goes the other way. I know now that this thing has to have x minus 1 as a factor. So x minus 1 has to divide evenly into this polynomial. Because of this fact, I know x minus 1 is a factor. So that means I can write 2x cubed minus x squared minus 7x plus 6 as x minus 1 multiplied by something. And like, if you like right now, I'm right above those vertical spaces in the text near the bottom of the page. I know that this thing should factor as x minus 1 times something. Let's think about degrees. What's the degree of the polynomial on the left of this equation? 3. Biggest power on x you see is 3. This is a degree 1 factor. That means the biggest power on x I can see here is 2. This thing is a quadratic equation. If I can do this factoring, then I know that I win. I'll get a solution at x equals 1, the one I already know. I can set this equal to 0 and solve using the quadratic formula. All right, so here's the question. How do I find that something? And I'm going to propose 3 techniques. One of them is going to be very ad hoc. I'm just going to try to brute force a factorization into the polynomial. If you like, maybe this would be called factoring by grouping. It will be the technique that will take the most time and effort to learn, but it's also the one that involves the least technology. If you remember the goal, you can figure out how to do it. The one that I'm going to do in the middle column is going to be polynomial long division. How do people feel about polynomial long division? How do people feel positively about polynomial long division? How many people feel negatively, but you've done it at some point in the past? Okay, cool, that's about where I expect people to be. How many people haven't seen the idea of dividing a polynomial by another polynomial? Cool. For those of you who want a recap of what polynomial division does and how you do it, there are a few options. There's an appendix in the book on it, which does a good job describing it. So grab the textbook, go to the appendix on your own time. I've also recorded about another lecture's worth of recording going through some more examples of polynomial division. But we're going to do one example right now. We'll see how it goes. So, how do you find that something? Here's the first technique. So I'm just going to try to gather things together so that I see some things that I can factor an x minus 1 out of. So I'll start with the polynomial that I'm interested in. That is 2x cubed minus x squared minus 7x plus 6. And I'll try to do things to that while still being equal so that I just see some things that x minus 1 factors into. And I'm going to start with the highest degree term. I see a 2x cubed there. If I saw 2x cubed minus 2x squared, I could factor the 2 and the x squared out, I'd be left with an x minus 1. So I'd really like to see a minus 2x squared next to that 2x cubed. Do I see a minus 2x squared next to that 2x cubed? Well, I guess it depends on how willing you are to see things that could be there but aren't there yet. Because I could just put a minus 2x squared next to that thing, right? As long as I do the opposite. So let's do that. This is the same thing as 2x cubed minus 2x squared plus 2x squared minus x squared minus 7x plus 6. Do you agree that those two things are equal? All right, the two things in yellow, they just cancel anyway. So those two things are equal, but I put that there for a reason. Put that there because now those two terms that I put some parentheses around Well, I can do some factoring there. If I just look at that piece, everything there has a 2 next to it, so I can factor a 2 out. How big a power of x can I factor out of that? X to the power 2, x squared. And when I do that, I'm left with x minus 1, which is good. That's the factor I want to pull out. And now let's just see what we can do with the rest. 2x squared minus x squared, what does that work out to be? X squared. And I'm giving myself some space here. Minus 7x plus 6. So, here's the game. I've now factored out an x minus 1 out of the biggest part of the polynomial. I want to still factor an x minus 1 out of the rest of the polynomial. Let's start with that x squared. What would you like to see next to that x squared in order to factor an x minus 1 out? Yeah, a minus x would do the job. Can I just put a minus x there? Well, I could, as long as I put a plus x after that.
But why is it plus x squared?
Why is that plus x squared? That came from combining those two terms.
Okay.
So there was already a minus x squared. I had to put a plus 2x squared because I wanted to put the minus 2x squared. Cool. So now we're going to play a game that's very similar again. There's a piece that I made choices so that I would know for a fact that I can factor an x minus 1 out of. Do you agree that an x minus 1 is going to factor out of there? Awesome. I guess those two terms together will simplify to a minus 6x. But we'll deal with that when we get there. So, in the meantime, go to the next line, put an equal sign, and write down what that is equal to. Equals 2x squared, x minus 1. The thing in parentheses, how's it going to factor?
X times an x minus 1.
X times an x minus 1. So you can definitely see that an x is going to factor out. Everything there has an x next to it. Oh, I need a plus sign. X times x minus 1. All right, that's good. I want to see x minus 1's next to as much as possible because my goal is factoring out an x minus 1. And what am I left with? X minus 7x is minus 6x. Oops, don't want a double negative. Plus 6. All right, so that leaves me with minus 6x plus 6. Is there a way to factor an x minus 1 out of that? Yeah, cool. In fact, I'll like the rest of the things, but I'm going to start right below this. I want to factor an x minus 1 out of that piece. What do I need to multiply x minus 1 by to get the thing up there?
6 times x minus 1.
6 times. In fact, I want minus 6 times something. Because there's a negative and a positive. All right, now I'm going to copy these down. Ooh. Everything now has an x minus 1 next to it. I can factor out an x minus 1, and that was the whole goal. Equals 2x squared plus x minus 6 times x minus 1. I know what that something is now. What is that something? Well, it's on the board, right?
2x squared plus x minus 6.
Nice. I wanted to get x minus 1 times something. I guess I have something times x minus 1, but happily multiplication is commutative. if you try to do algebra in a setting where multiplication is not commutative, some things get way more difficult. Commutative means like you can write things in either order and they get the same value. All right, so let's analyze some things about this technique. There was an algorithm I was following, right? I started at the biggest terms. I tried to see how I would want to, what I would want to subtract and add, or add and subtract, so that I could factor out an x minus 1. A bunch of these terms, as soon as I got this x minus 1 times 2x, I just kept on copying it down again and again. So somehow that's like, in order to run this algorithm, I needed to, but that felt inefficient. This algorithm is going to take up the most space of the algorithms we developed today. And it's also going to be the one that'll take the most time. And mainly that's because you keep writing down the same thing over and over again. So, inspired by this, in the next column, let's do some polynomial long division. Because right, division is what I want to do. If I have a thing that I know equals a thing that I know times something that I'd like to know, I just want to divide this x minus 1 to the other side. That's all I want to do. But then how do you actually perform that division? Well, you can do this factoring by grouping to pull it off, or you can use polynomial long division. So this is going to be more efficient than this technique in terms of space and in terms of time. Maybe I'll see how people did like even space-wise. I know there was like slightly limited space in that box that I provided. Did anyone like get themselves into lots of trouble and now they need to just rewrite those notes so they're readable? Oh, that surprises me. I don't think I would have been able to do that. On the other hand, like it's probably worth rewriting this if you want to like internalize the strategy a little bit more. Let's do polynomial long division. So if I want to do long division, I'll even use the same notation as when you do long division with numbers. I want to take 2x cubed minus x squared minus 7x plus 6. And I would like to see what happens when I divide x minus 1 into it. And the algorithm I'll follow is going to be the same as the algorithm you use when you do long division with numbers. I'm going to look at the biggest piece in the thing in the box. I guess that's the numerator. And the biggest thing in the denominator, I'm going to compare them. That's going to tell me what I need to multiply by. And then I'm going to do something where I like multiply the thing I put here by that, and then I need to subtract it. So I don't know. How do people feel about long division of numbers? How many people want me to do a long division of numbers because they forget what that even means? Okay, cool. I will. How about this? 3 divides evenly into 72. That's a true fact, right? So how do you do long division? You take the biggest part of the thing in the box, and you go as far along as you need to get 3 to go into it. So let's do that. How many times can 3 go into 7? Twice, because then you get 6. If you did it again, you get 9, which is too big. So you put a 2 there. 2 times 3 is 6. And then you subtract it because you want to see how much more you still need to do. So you carry that 1 down, you bring this 2 down. How many times does 3 go into 12? 4 times 3 is 12, you do subtraction, you get 0, denominator is 0. So I'm going to do that exact same thing, but with polynomials now. And it will in fact be easier in some ways, because I only need to pay attention to the biggest part of both. What do I need to multiply x by to get 2x cubed? 2x squared. And right, like that's an easy question to answer. There's no 2 in front of me yet, and I don't have enough x's. So now I multiply 2x squared by x. The step that I'm about to do is going to involve distributing a negative sign. So if you walk exclusively in pen that you can't erase, hold off on writing until I tell you to. 2x squared times x is 2x cubed minus 2x squared. Then you need to subtract that result. That's too hard to walk with as is, so I'm going to distribute the negative sign. Now, if you're a pen user who doesn't like erasing, that's what you write down. Fair enough? And now, just like you do subtraction here, we'll do that subtraction. 2x cubed minus 2x cubed is 0. I knew it had to be, that's why I picked 2x squared to put there. Negative x squared plus 2x squared is plus x squared. And let's notice that's the same as that x squared that showed up. Feel good so far? Now, we just keep on doing that. What do I need to multiply x by to get x squared?
X.
Yeah, right? And that's like another one of these questions that's like an automatic answer. Like the answer is in the question as long as you know what squared means. Multiply x by x minus 1. That'll give me x squared minus x. I need to subtract that. So, distribute that minus sign. That's just to make it easy to do the subtraction. X squared minus x squared is 0. That's good. I knew it had to be. Oh, that was just a straight line from what was written there before, right? There's not a fifth power of x anywhere? Okay, that's good. So a fun thing with this is you need to make sure that your polynomials are written in descending order of powers for this algorithm to work correctly. If you did have a 7x to the fifth in the middle of the polynomial, it should have been at the front. Anyway, carrying on. Minus 7x plus x is minus 6x. So now I keep going. What do I need to multiply x by to get negative 6 multiplied by x?
6.
Well, negative 6. And now I iterate. Negative 6x. Negative 6 times negative 1 is positive 6. But I need to subtract that result. And maybe you can see now that if you don't do this, like draw the parentheses and then distribute the negative sign, it's really easy to lose track of how many negative signs there are because there are like 3 negative signs attached to that 6. So distribute the negative sign. Negative 6x plus 6x is 0. I knew it had to be. 6 minus 6 is 0. But I knew that had to be 2 because this should have a remainder of 0 after I do the division. All right, so let's notice something. If you were to do the algorithm, this was less walk than that. And you had to write a little bit less down. It probably took about the same amount of space, maybe a little less space on your paper. But there's still like a lot of wasted space, right? I didn't use any of that vertical space. Since I had to write those in order anyway, like those powers of x were actually just wasted space that was taken up that I didn't need to put there, really, as long as I just knew that I had to have powers of x there. So the idea of synthetic division now, oh, maybe I should say this next. How do people feel about synthetic division of polynomials? How do people feel like it's at least something they've seen in the past? How do people even feel positively about it? Yeah, cool. Synthetic division, if you're in a situation where you can do it, and you don't mind writing something down that only means something to someone if they already know the solution, then synthetic division is great. So let's do some synthetic division. So here's the algorithm for synthetic division. The idea of synthetic division is, I didn't actually have to write all the stuff on this side. So here's what I'll write instead. 1, 2, negative 1, negative 7, 6. So what did I put in here? I put the coefficients of the numerator. And right there, I just put the root that corresponds to the denominator. So instead of x minus 1, I just put a plus 1 there because that's the root of this thing. And here's the algorithm that I'll follow. And maybe I'll point it out while I did things over here. So synthetic division assumes you had a 1 in front of that x, which we did in this case, so we can use synthetic division. What did I need to multiply by this 2x cubed? Well, it was just this 2, and then the appropriate power of x. So first step in synthetic division is copy that 2 above. And that just corresponds to the question of what do you need to multiply x by to get 2x cubed. The algorithm from here is take this 2, multiply it by the 1, put it there, and now add that column. That corresponds to that 1x squared that shows up. So take that 1, I'll put it right here. 1 times 1 is 1. Negative 7 plus 1 is negative 6. So the algorithm in synthetic division is you start by taking this biggest number off, copying it above. And by biggest, I mean the thing that's next to the x cubed. You take that number, you put it here, you take 2 times 1, put it there. You do addition in that column. That gave me the 1, I put a 1 here, 1 times 1 is 1, do addition in that column. I get a minus 6 goes here, do addition in the column. And this took up way less space, right? But it kind of took up way less space because I just didn't tell you what any of the symbols mean. So that's the idea of synthetic division. If you write down the minimum amount to do the algorithm, you can save some space. So, by the way, there are the 3 different flavors of doing polynomial division. You can factor by grouping, you can do polynomial line division, you can do synthetic division. They'll all get you to the same end result. We have enough time now to actually solve this polynomial equation. I think there's space at the top of the next page. Let's now do it. So, if I wanted to solve 2x cubed minus x squared minus 7x plus 6 equals 0, that's too hard to solve directly. So instead, I now factor. This factors as x minus 1 multiplied by 2x cubed plus x minus 6. Yeah.
Isn't it x squared on the 2x?
Yes. Yes, it is. Did I say cubed? Yeah. Okay, that was a mistake. The degree should go down by 1, otherwise what's the point of this? You didn't make your life better. All right, does that look easier to solve now? Yeah, I can split this into 2 equations. I got x minus 1 equals 0, or 2x squared plus x minus 6 equals 0. That tells me that x equals 1 is a root. That is not impressive because I knew it was a root already. That was like the seed information that I started with. 2x squared plus x minus 6, does that look like something you can set equal to 0 and solve? Yeah, what technique would you like to use? De factors, that's nice. How many people would have the intuition to use the quadratic formula instead? That's good too. Should I go through either the walk of finding the roots of that degree 2 polynomial? Or should I just wait? Should I do the walk? Okay, I didn't see any hands go up, so I'm going to be quiet until someone tells me what the roots are.
I got -2 in 3 seconds.
Sorry, it took me a second to parse out what you said there, but that's what you meant, right?
Yeah.
Okay. Do I hear a second on those being the roots? Cool. Let's just do one last sanity check. That was a degree 3 polynomial we started with. How many roots did I expect? Just 3. Those are 3 roots. So we found all of the roots. This accomplishes the task. If you're feeling ambitious and careful, are there some things you can now do to check if those are actually roots? Graph it? Sure, that'll do. You can also, you have a calculator, directly plug in those inputs. The point is, there's no reason to ever have incorrect answers. Unless you really just gave up. In which case, you should have asked me some questions. All right, so we have some amount of time left. There are like 2 examples on the next page. I think I want to do one and leave you to do one. Page 67. x cubed plus x squared, so, well, first one or second one. So take a look at those. Which one would you rather see done? The one that's higher up the page? X squared plus x cubed plus x squared plus x plus 1? Cool. The second one, which has some bigger numbers. Cool. Seeing more hands with bigger numbers, we'll prioritize that one. I think we have enough time that we can get that done. So, let's solve. You have it all written so that I can borrow space. Let's solve the equation. 2x cubed minus 10x squared minus x plus 5 equals 0, given that x equals 5 is a solution. Since x is a solution, since that's a solution, I know x minus 5 is a factor. So I should be able to pull an x minus 5 out. I'm not going to do it all three ways. I'm going to pick one. And I'll let you all pick which one I should do between polynomial long division and synthetic. Should I do polynomial long? Should I do synthetic? Cool. I think I saw slightly more hands for synthetic. I will do synthetic. If you want to do polynomial long division, do it. And you should get the same answer as I do, as long as I do it correctly, because I assume you're going to do it correctly. So, let's do synthetic division and see how it walks out. So, there's the numerator. 2, negative 10, negative 1, 5. And I'm going to do a quick sanity check. When you do synthetic division or polynomial long division, you need to be careful if there are any like just missing powers of x. Then you need to throw some extra zeros in there. Any missing powers of x? That's good. 5. X equals 5 is a factor, so I'm going to put a 5 there. Now I will run the algorithm. If you're doing polynomial long division, keep on going on your own. Step 1, the 2 comes up. Now I multiply 2 by 5, I get 10, put it in the next column. What's negative 10 plus 10? So I put a 0 in the next column, and I keep on going. 0 times 5 is 0. Negative 1 plus 0 is negative 1. So I put a negative 1 in the next column. Negative 1 times 5 is, and when you add that last column, what do you get? And that last column corresponds to a remainder. If you're in a situation where you know it should divide evenly in, which we are today, then you know the remainder should be 0. Still compute the remainder, because if you like screw something up in the computation, it's going to screw up your remainder term. So think of that remainder equals 0 as a checksum. I believe that this is correct now. So that means that instead of setting that equal to 0, I can set x minus 5 times 2x squared minus 1 equal to 0. Gesundheit. Those of you who did polynomial long division, did you get the same 2x squared minus 1 showing up? Okay. That's good. I saw a few heads nod. Does that look easier to solve? Yeah. It looks like I got x equals 5. The not impressive result. And 2x squared minus 1 equals 0. Gosh, 2x squared equals 1. X squared equals 1/2. X equals plus or minus square root of 1/2. Which, if you want to simplify, simplifies down to plus or minus root 2 over 2. Have we now found 3 different roots? And that's the number of roots I expected. That makes me happy. All right, so I have contacted LTS. They should be by inside of the next 10 minutes to fix the projector. That's too late for your benefit today, but tomorrow we should have a projector. I do plan on posting this thing that happened as a recording. I'll also post a link to last year's recording just because I know this maybe felt a little bit off.
Where did this come from?
Yeah, so I have a minus x squared already, plus 2x here. Yeah, like, go book that has an appendix. Yeah.
This is a no-no.
Well,
It's not, the cables are not nearly long enough to do that.
well, no one can see the screen if I don't. Like,
No, just so you know, if it goes out,
that,
it's not, nothing I can do.
okay, I mean, the monitor seemed fine, like it was fine.